Good morning and welcome at today's first press conference about the gravity measuring satellites GOCE and GRACE. We have invited 4 scientists who've had and still have a leading role in the satellite missions of GOCE and GRACE and the subsequent research. On GOCE we have Rune Flobergagen and Per Knudsen. Rune Flobergagen is the GOCE mission manager who works for the European Space Agency, and he will present the second gravity field model from the GOCE mission and some of its application areas in science and for society at large. We have Per Knudsen. He is the head of geodesy of DTU Space, Denmark's National Space Institute. He will present the data he used on the GOCE satellite mission to accurately map the details of the mean ocean currents. He also will show maps of the ocean currents and explain how they are derived in general. On GRACE, we have Frank Vlechtner and Jürgen Kusche. Frank Vlechtner is the GRACE principal investigator and he works at the Helmholtz Center Potsdam in Germany. And Jürgen Kusche is a professor in geodesy at Bonn University and also a coordinator of major interdisciplinary space programs, of which GRACE is of course an important part. And well, together Frank and Jürgen will show a selection of recent results obtained in 4 fields with GRACE, and they will also describe the road to a GRACE follow-on mission to be launched in 2016. Please go ahead.
So good morning. My name is Rune Flobergagen, as the introducer said, from the European Space Agency. What we are showing first of all here today are the results from the GOCE mission, and GOCE stands for Gravity Field and Steady State Ocean Circulation Explorer. That means obviously that the mission is about the gravity field and what you can do with that in all kinds of applications and for society at large, and it is also certainly about ocean circulation. My colleague on my left is going to present the ocean circulation part, and I will take care of a good deal of the other elements. Now, gravity is something that is a little bit abstract for many people. Gravity is everywhere. It is also somehow nowhere because nobody really knows exactly what gravity is. It is easy to understand because we experience it every day, but it is also very complicated to understand. What we are presenting here are results, let's say, in terms of gravity field mapping for our own planet, the Earth. And therefore we are not looking at gravity and gravitation from a fundamental physics perspective, but from the perspective of Earth science and, as I said before, the use of this information for society at large. And obviously I will spend also a couple of minutes on explaining why that is important. Now, what has GOCE done? What is the main result from GOCE so far is quite, let's say, briefly put, is that we have produced the best ever gravity field map from space. We are looking at high resolution in terms of spatial resolution, variations of the Earth gravity field that have never been seen before. That is the achievement of the GOCE mission at the end of its nominal lifetime, which took place at the end of February, and the mission is still healthy, and we are continuing to measure. And of course, in the case of gravity, the longer you measure, the better your high-resolution image, if you will, of the variations of the Earth gravity field will be. Now, why is this important? Well, what we show here in this picture is a picture of what we call the geoid. Geoid is perhaps from some people kind of an abstract concept. But what you can actually consider it to be is like an enormous or gigantic water level that applies to the entire Earth. Because this geoid, which is defined by the gravitational potential or by the gravity field, if you will, is in fact the surface that defines the horizontal everywhere on this planet. It means that heights are not measured with rulers, but heights are actually best measured with gravity and changes in gravitational potential or energy, if you will. The surface is also, let's say, equal level everywhere. That means heights, as I said, are best defined using gravity. And with this surface, we are able to combine measurements of height all around the globe in a way that was not possible prior to this mission. This surface is also coinciding in its definition with some sort of idealized ocean. It means that if you consider an ocean that is not subject to wind stress and to solar irradiation, if you will, this geoid is basically coinciding with that particular ocean surface, and I'm sure that my colleague on my left will go into more detail about that aspect. Now, what you see on this image of the geoid is basically the deviations of the surface with respect to an ellipsoid, that is the ellipsoid that best fits the geometrical shape of the Earth. And you will see that there are variations in this that are in the order of plus and minus 100 meters. For example, if you cross the Indian Ocean from the east coast of Africa, or from the Horn of Africa towards Southeast Asia, you will enter into a, let's say, geometrical trough of about 100 meters or so. Still, you do not move on the same surface, or let's say, in terms of energy. That means if you put a marble on the surface, it will simply not roll. So why, let's say, before that we come to the point of why that is important, we'd like to emphasize a little bit what kind of sensitivity we're talking about in the case of the GOCE emission. So what I'm depicting here are basically the constituents of the G-force, say the gravitational acceleration on the surface of the planet. And we all know from school that, let's say, if you take the Earth as a homogeneous sphere, you basically get on the surface of the planet an acceleration which is about 9.8 meters per second square. If you go a little bit into, let's say, zooming in on what is actually the case, the next thing you will realize, and this is not new, of course, is that the Earth is rotating and it is behaving a little bit like a fluid, which means that it is kind of flattening, and this flattening basically gives variations in the second decimal of the of this gravitational acceleration. Now, if you also consider that, of course, the gravity field is, if you will, like a mirror of the density variations or the mass distribution inside of our planet, you can move on a little bit and look at what is the effect of mountains, for example. And then from mountains, you will see variations in the third digit. Going deeper down, let's say, into the Earth, we have irregular distribution of mass inside of the Earth interior, and they tend to show up, let's say, in the fourth digit or so. Now, we can continue further. We can look at what is the effect of the hydrological cycle, which is something that the gentlemen on my right are going to talk more about. I'm pretty sure about that. We can look also at the effect of big buildings or humanly, let's say, constructions built by humans. They tend to show up in the seventh digit or so, if they're pretty big. What GOCE is actually doing is that we are measuring to, let's say, 1 part in a million, the variations in the Earth gravity field. So we are, if you like, let's say, at a level which is about 1 order of magnitude above, let's say, what actually has been built by humans on this planet. This is the type of sensitivity that we are talking about. Now, as I said, these variations in the gravity field are due to variations in the mass distribution inside of the Earth. Mantle convection, mountain building, plate tectonics, and so on. And all of these processes are, of course, better understood and benefit from a better understanding of the Earth gravity field. So why do we care? Why should people in general care about this? Well, I put up here, let's say, an example of, let's say, the gravity anomalies or gravity variations. That's on the bottom right of this particular plot for the area of Japan. And you will see here that, let's say, when you go from red to blue in this, this plot, it means that there are big variations in the Earth gravity field. And these variations are, of course, related to the complicated tectonic situation that we have, let's say, in the Japan Sea. And it is obvious that with a better understanding of the Earth gravity field in this sense, we are going to be able to better understand the mechanisms behind these earthquakes that are, have had and will continue to have a devastating effect on the lives of many, many people on this planet. There's one example. Another example is that, as I said already earlier, the Geoid, it defines, let's say, an idealized, or it is an idealized reference frame for measuring heights all around the world. Today we have around the globe about 200 or so different height systems that are being used. They are using different concepts, they are using different datums or 0 points, different definitions if you will, and they have different errors, different quality. So that means that if you would like to understand what is the height of a particular mountain, for example, or the height of a particular protection system, or the height of a bridge or of a tunnel, with respect to the reference system of another country, in general, it tends to be a pretty delicate matter. One example is the construction of the tunnel underneath the English or the British Channel. People started to drill from both sides, from the UK side and from the French side, and when they arrived more or less in the middle, they found out there was a 50 centimeter difference in the height on the two sides. And so these things also have practical importance for construction work, obviously. So actually what we are trying to do with this mission is to make an effort to define a common height system for everywhere around the globe. And that's important not only for construction work, but also for things like the understanding of sea level rise and increases in sea level or decreases in sea level all around the globe in a global context. I cannot hand over to my colleague before, let's say, focusing a little bit on how we did it. GOCE is a very special satellite. It is flying extremely low. It flies at an altitude of only 255 kilometers. It means it needs to have particular systems on board that allows it to keep this altitude, simply because at this altitude there is still pretty significant residual effect of the Earth's atmosphere. And if we would not have a drag compensation system, the satellite would simply fall from the sky within weeks. It is also a satellite that has wings, much like a commercial airliner, if you will, and that is because the little bit of aerodynamic pressure that there is, it helps us gain some sort of aerodynamic stability of this spacecraft. The measurement concept is very simple. This is my last slide, in fact. What we are measuring in this satellite is basically the relative acceleration or movement of test masses, we call them. In this picture, they are simply denoted as oranges or grapefruits, I'm not sure. This is a picture of a cosmonaut that receives oranges from a supply ship, and what he actually is doing, apart from playing them, is that he is observing the relative motion of these test masses inside of the space station. And GOCE is a similar thing. We are observing and measuring the relative motion of test masses over a distance of 0.5 meter inside of a satellite, and we relate that to the difference in gravitational attraction at the points of these two oranges. Now, in concept, it's very simple. Doing that at a precision of 10⁻13 G or so, that is, of course, the tremendous challenge that this mission has been able to achieve. So, that's my last slide. The gravity field information that we are delivering is going to be used and is already used in nearly all the earth science disciplines that are looking at surface processes, let's say processes that do take place on the surface of our planet and also in the Earth interior. And as the mission continues, we will see more of this. Thank you very much.
Okay, can I get the mouse here? Okay, yes, thank you very much, Rune, for giving me the chance here, because now I will continue and explain a little bit about the use of GOCE in oceanography. As we already can see on this picture here, we have some errors marking the Gulf Stream. This is, I think, in Europe one of the most important currents, because it brings us heat. And make sure that, especially in the Nordic countries where I live, that we have a temperature that is nice. But without it, it would definitely not be that nice. So this is one of the things that we could actually go in and analyze here. But let me show this picture here, because this is actually what GOCE has really brought us in terms of new things, because using the new data from GOCE, we have actually been able to map the ocean currents like we can see it here. It is the first time we have been able to map the ocean currents to that degree of detail with an accuracy where it is very, very good. So this is the breaking news with respect to oceanography, and this satellite has brought us so far. I'll go a little bit more into detail with what we actually see here, but naturally we will see the main ocean current systems here. As I mentioned, I will show them a little later, but definitely we can also clearly see the equatorial currents and the stream around the Antarctica as one of the major ones here. But why is that so important? Well, we all, and especially in oceanography, would like to know all the details about the ocean circulation and transport, as I mentioned before. There are still a lot of processes that are not fully understood, and that makes it very difficult to actually use information normally collected about the ocean to predict things about climate, for example. We can see here the main current systems on this plot here. We have all the warm currents, as I was explaining before, as the Gulf Stream, but certainly there are also cold ones, which are the blue ones here. So this more or less reflects or show how the currents are transporting water and heat around in the oceans. If we go a little more into detail, I mentioned climate change. This is of course important for us to know, and for society as well. How should we adapt to climate change? The ocean plays a huge role in that, and we really need to understand the circulation to be able to predict that. On this graph here, at least on the right, we have both the surface currents marked in red here, but we also have currents deep in the ocean, and we need to build up mathematical models for actually trying to describe the state of the oceans and how it will react on climate change. For example, what happens when sea ice disappears, if it is disappearing, and what happens when water is melting from the ice cap in Greenland. How is it going to be distributed in the oceans? Those issues are definitely things that are important to know. That leads me to the perspectives of this, because we are still in these are objects to research, but definitely it is important, as I mentioned, to have this knowledge to be able to forecast the impact of climate change. There are other issues also, because society is actually having a lot of other activities where these services and knowledge is important, and operational maritime services is one of them. It will be better able to estimate ocean currents, which is needed for ship routing to save fuel, and also, of course, for making it as efficient as possible. But also fisheries will benefit from services like this. Also, on the much more dramatic side, we have safety as an issue that this will be very useful. We have disaster management, where an improved modeling of the oceans will be crucial to actually both facilitate search and rescue, but also oil spills, for example, and other types of pollution. Where is it drifting, and how should we actually come about it? So those are mainly the perspectives here. Just a few words on how it is done, because these new information, the ocean currents, are derived together with other types of information acquired using satellites. Because we have for years been measuring the sea surface heights from satellites, and it is actually by merging these two types of information that we can get the ocean currents. One important thing is that using the satellite information, we actually have global coverage. There are many places in the world where we know a lot about the currents, but there are even more places where we do not know that much about it. For example, in the Southern Ocean, pretty hostile environment down there, and especially in sea ice covered regions where it is very difficult to acquire data. But this is, I'll just go on showing a few of the examples here. If we look at the Gulf Stream, as I mentioned before, some of the light blue colors here are actually the new things that we can see that we have not been able to see using similar techniques before from space. We can see also in the Kuroshio Current here that we have many details to look at. If we continue with a few more examples, the Agulhas south of Africa is a very huge current system also, which is important to know about. And that's the same thing with the Brazil-Malvinas confluence system over at east of the South America. I mentioned the Antarctic circumpolar current. This is of course important because it is a huge current system, very important for the climate system and the impact of climate change. We have been able here to identify more fronts and more details about the currents that will be important for the assessment of the impact. So just the final slide here. I mentioned that the satellite systems can give global coverage of information to be used both for monitoring oceans and use the information in services for both the maritime and other groups in the society. The important thing here is of course also that GOCE is a very important step in developing this observation system to be spaced only and to actually have a very much strengthened infrastructure for the observation system. So that concludes what I would say. So, thanks.
Okay, thank you, Per. I think I then can take over coming to the GRACE satellite mission. My name is Frank Flechtner from the German Research Center for Geosciences, and I'm the co-PI of this mission. GRACE is the abbreviation of Gravity Recovery and Climate Experiment. In contrast to the GOCE mission, our satellite experiment consists of 2 satellites, totally identical, and the test masses in this experiment are the satellites itself. So they are departed by about 220 kilometers in space, and what we are doing is to observe the range and the change in rate between these 2 satellites, which is depending on the changing mass distribution underneath, with the thickness of the human hair, less than the thickness of a human hair. So this is a few micrometer, which is quite impressive. As I already told, it is a twin satellite mission. It is a US-German project, so a NASA-DLR cooperation. It was exactly 7 years launched before the GOCE satellite mission, so 17th of March. It is a lucky day for gravity field mission. And the PI on the US side is Professor Byron Tapley from the University of Texas. As I mentioned, we have celebrated the 9th birthday a few weeks ago. But the, let's say, bad news are that, of course, the satellite mission will not go forever. So depending on the instrument and especially the battery status and the solar activity, we expect that the mission will end in about 1 to 4 years. So it's hard to predict this, but it is clear that this mission will end at some time, and the valuable time series will end at some time. And at that stage, I have to say that the overall, let's say, goal of the GRACE satellite mission is not, like in the case of GOCE, to make a very precise snapshot of the mean and static gravity field, but to observe the mass changes within short time periods, for example, monthly or weekly time scales. And from these snapshots, you can get, for example, trends or annual and semi-annual behavior of, let's say, the contributors to mass distribution in the Earth system. So therefore, we are already planning GRACE follow-on mission, which shall be launched in 2016. So I will come back to that later on. As a quick fact, we had about 2,700 users for the GRACE mission, so you can see it is a very highly successful mission. We have more than 700 publications, very much in Nature and Science magazines. We have founded a very large interdisciplinary research program in Germany called Mass Transport and Mass Distribution in the System Earth, where Jürgen Kusche is the coordinator from the University of Bonn. And he will show you later on some recent results. GRACE initiated interdisciplinary research between hydrologists, glaciologists, oceanographers, geophysicists, geodesists. The major breakthroughs of our mission is that we have now a very clear understanding of the changes in the terrestrial water cycle, that we can observe the melting and the growing of glaciers and ice sheets. We can observe sea level rise, and especially what are the causes of this sea level rise. Is this ice melting into the oceans, or is it thermal expansion? So we can clearly distinguish between these different effects. And like for the GOCE mission, we are using our static gravity field to make some investigations for solid earth physics. For example, we can observe the past glaciation. We can also observe large earthquakes. And I can only make, at this stage, some advertisement for the session G5.3, where we have a poster session on Thursday and oral presentations on Friday. So this is once again highlighting the results of the GRACE mission. On the top you can see, let's say, a time series of 12 monthly gravity fields showing the mass variation in the Amazon. And on the left-hand side you can see a snapshot of a static mean satellite only and combined gravity fields, which has of course a much larger spatial distribution, but only, let's say, no time variability in. And with that, I would like to hand over to my colleague Jürgen Kusche, who will show you some examples showing the breakthroughs in the understanding in many disciplines.
Okay, as it was already explained to you, the main goal of the GRACE mission is to monitor the temporal change in gravity. We're not that much after a mean, a static high-resolution gravity field. Now, according to Newton, change in gravitation, or gravitation itself, is caused by mass, and change in gravitation must be caused by changes in mass. Now, changes in mass at the time scale of a couple of years that we're looking at with a satellite mission are almost entirely occurring at the surface of the Earth. Or basically, it's all the moving around of water at the surface of the Earth that we're talking about, within the atmosphere, within the ocean, and within the continents in form of groundwater and surface water. So what this image shows you is what we obtain from the change of gravity from GRACE in terms of water mass, basically. What you can see here is, on a global perspective, for instance, the large annual changes of water mass in the large hydrological basins like the Amazon and in the Zambezi and Congo basins in Africa, or for instance in Siberia, where you have heavy precipitation. You can also see changes of mass over Greenland and over Western Antarctica, for instance. And I'm going to talk about this in detail in a moment. Okay. In the domain of the terrestrial water cycle, research with GRACE has mainly focused on two directions. One of them at the smaller scales, we have been able to show that GRACE can see man-made changes in the terrestrial water cycle, in particular the groundwater pumping for agriculture. This has been shown already for India a couple of years ago. This is an example from a publication of Famiglietti, where they show the decline of groundwater for the Central Valley of California during, well, with the onset of a drought at about the year 2006 and onwards. At the larger scales, at the global scale, we're looking at the terrestrial water cycle from a more climatic perspective. And GRACE has been able, for instance, to show that there is in general, there is a decline of water, or in this case, snow mass volume in the Eurasian river basins, which goes along with an increase of water mass or snow mass equivalent in this case for the North American basin. So it's a very large-scale transport of mass, which of course would be extremely difficult to observe with the usual terrestrial techniques. Then, within the cryosphere of our planet is a very sensible indicator of climate changes. And GRACE has in the past already proven to deliver estimates on how much and at which rate the ice sheets and also the glaciers decrease in mass, and what this means in terms of sea level rise. Now, the good message after several years of GRACE mission is now that, first of all, the estimates are really converging. You know, when different researchers look at different timescales with different data processing, they don't always end up with the same numbers. But here we can see that, in this case, for Greenland, the estimates are really converging to a rate of overall mass decrease in the order of 200 gigaton per year from GRACE, but also from other techniques. On the right-hand side, you can see estimates which are actually not from GRACE. This is from laser altimetry, a technique that samples the change in the surface of the ice sheet and converts these changes in surface height into mass changes. And basically, this technique gives us almost the same estimate. Now, what we also know from GRACE is now that the rate the Greenland ice sheet is melting is not completely uniform. You can see regions over here, this yellowish spot in the center of the ice sheet, where the ice sheet is in fact thickening due to a net increase in precipitation. We have regions to the south and east where we have a decrease. Over here we have a decrease, and we also know from GRACE now that the rate of the decrease is not uniform. For instance, in the southern east, the rate is decreasing, which means that the ice sheet is still melting, but it's not melting that fast as it used to do a couple of years ago. Whereas in the northern part, over here in the northern western part, the rate of the shrinking is increasing. So here it's taking up speed. Overall, averaged over Greenland, we find that the rate is still increasing. So there is an acceleration. Now, if you look at the behavior of the ice sheets beyond what happens, let's say, as a secular trend, and beyond what happens with the dominating influence of the seasons. So you take out the trend, you take out the dominating influence of the seasons. We are now able to show that you can see, in this case for Western Antarctica, a clear pattern of El Niño southern oscillation. After a certain lag, this oscillation index clearly maps into the increase and decrease of precipitation over the western Antarctic peninsula and the Amazon Sea sector. Okay, now for the ocean, GRACE delivers us changes in the mass of the ocean. That's the main target of the GRACE mission, also compared to GOCE over the ocean. We can monitor the volume change of the ocean for quite some years using a technique that is called altimetry. But the volume change differs from the mass change whenever the ocean is warming, and also whenever there are changes in salinity. So what GRACE gives us now is the opportunity to split up sea level changes into the causes. And for instance, in this case, Song and Kohlberg have assessed the deep ocean warming. Deep ocean means below 700 meters from the mass information from GRACE, which is something which is almost impossible to assess from other types of observation systems. And they found that this deep ocean contributes to almost 1/3 of the observed sea level change, which is a finding which would not have been possible without GRACE. For the Mediterranean, Fenoglio and all in a recently submitted study found that the Mediterranean is a sea where you don't observe any big sea level change at the surface. With altimetry or with tide gauges, observing the surface tells you there is only little change. This is what we have known so far. Now, GRACE told us that there is a mass change ongoing in the Mediterranean, which corresponds to something like 6 or 7 millimeter water level each year. And this mass change is counteracted mainly by an increase in salinity. And this is again a result which would hardly be possible to derive from local shipborne measurements of salinity alone. Okay, and finally, this is the fourth field of research what I'm talking about. With GRACE and with additional observation systems like GPS, monitoring the surface of the Earth with GPS, we're now able to assess geodynamic phenomena. And for instance, what Ivans and co-workers did for the Patagonian ice field and for the West Antarctic Peninsula is they were able, using GRACE and the height change measurements from GPS, to separate the present-day decrease of ice mass from the ongoing reaction of the Earth's crust due to past losses of ice mass. You know, we have had a number of ice ages in the past, and still the surface of the Earth is reacting to the ice, which is gone for a long time already. There's still an ongoing reaction, and this is one of the most difficult things to separate this effect from the present-day effect that we see in GRACE. And this becomes now possible with combining GRACE and GPS. Now here's another example for where researchers have been looking into the physics of earthquakes and the properties of the Earth's crust where these earthquakes occur. This is a result from the Chile earthquake that occurred in 2010, and Hahn and al. Had looked into the distance change between the two GRACE satellites where Frank talked about, and the green and the red lines in the center plot shows you the distance change before the GRACE satellites, before the earthquake occurred and after the earthquake occurred. And you can see clearly at the time of the earthquake and at the location of the earthquake, they have found a clear change occurring, which they are now comparing with models of the fault geometry of the earthquake. And this helps us to understand the fault mechanisms and the properties of the Earth crust.
Okay, I would like to finish our presentation with two more slides telling you, let's say, that the good news on the status of the GRACE satellite mission is that after already 9 years in space, the health of the science instruments is still very, very good. And also the solar activity, which is responsible that at one day the orbital height will go down and that the satellites will burn out in the Earth's atmosphere, is still quite moderate, so that we could hope that in principle the satellite mission will go on for another 3-4 more years. The bad situation, as I already told, is that the battery status is now quite poor, that we had seen that the capacity of the battery has diminished compared to the beginning of the GRACE mission, and that we have also some cells in the battery which failed or show signs of weakness. That means since a few months we have to operate the satellites by preventing overcharging the batteries, and that means that we have also to limit the power consumptions during certain periods, and that also gave us to the very sad situation that in January we had to switch off the accelerometers which measure the forces acting on the satellites due to the atmosphere and due to solar radiation, had to be switched off. And so for the first time during the mission we could not deliver a gravity field in that month. That gave us once again, let's say, the hint that we have really to start the design, the planning for a GRACE follow-on mission. And this shall be due to the very, very good technological scientific partnership between NASA and Germany, should be again US-German project with anticipated launch date in 2016. This follow-on mission should again monitor the Mars transport over at least 7 years of lifetime. This satellite mission will be some kind of clone of the GRACE satellite, so they will look exactly the same. We will, of course, introduce some lessons learned from GRACE, and we will add on a laser ranging instrument which shall measure the distance and the distance change between the two satellites about a factor of 20 better than the microwave tracking system which is operated on the GRACE satellite missions. And this is more or less linearly giving a 20 times better gravity field for the follow-on mission. We will also fly an improved orbit. This will be a little bit lower than the current GRACE orbit, which is about 470 kilometers. So the planned height is 410 kilometers, because you can imagine that the lower you go, for example, GOCE is flying on 255 kilometers, the more sensitive the satellites are on gravity signals. And the second change in orbit will be likely that we will fly a so-called pendulum orbit, that we do not observe the gravity change in a long track direction, in the flight direction of the satellites, but also cross-track to the orbit. And let's say my final comment is that I'm a little bit sad that we could not say today that the funding of this follow-on mission is settled. We are still in discussions on the US side, but especially on the German side, to get the funding for the German contributions, which will be the launcher system, and especially the laser ranging system, which will be built by German technology and of course German money. And we hope that we will get a final decision by the two ministries which are involved in the decision process. This is the Ministry of Education and Research and the Ministry for Economics, that we get a decision this month and that we get the mission confirmation review in August this year. So this is my final statement. Thank you.
All right. Thank you for your presentations. Are there any questions? Okay, then, yeah.
This isn't really a question. I'm Ann Cairns from the American Geophysical Union, and the question that was running through my head the whole time you were talking was how valuable this information is and concern about funding. And I just wanted to make a quick comment that AGU has begun to really monitor what's happening in the funding environments and to speak out and advocate for particular technologies as much as we're able to. So we'll do our part.
Certainly appreciate it.
Okay, well, if there are no more questions, I'd like to end the press conference, and thank you for your attention.